In October 2005, NASA's Constellation program chartered the Exploration Launch Projects Office to begin developing safe, reliable, and affordable space transportation systems to position America for continued leadership in space. Since it was formed 10 months ago, the nationwide ARES launch vehicles team has made measurable progress both in long-term planning and early hardware design and testing. For example, conceptual vehicle designs are being validated in a variety of ways, such as wind tunnel testing at NASA and contractor facilities across the country, including the Langley Research Center, Ames Research Center, Marshall Space Flight Center, and Boeing's facility in St. Louis. Converting two-dimensional drawings into three-dimensional wind tunnel models gives rocket engineers confidence that vehicle designs will perform as expected in real-world flight conditions. Almost 1,000 wind tunnel runs have been conducted across a range of flight speeds using various sized models. Adding geometric details such as booster separation motors and the reaction control system projections that cause drag provides a vast amount of early data to the aerodynamic database being created by the ARES system. Wind tunnel analysis is backed up by other state-of-the-art tools such as computational fluid dynamics. The launch abort system on top of the Crew Exploration Vehicle capsule is designed to move the astronauts away in case of a launch emergency. The Ames Research Center has developed computer models that help designers understand what would happen during various situations when the rocket crew capsule combination is on its way into orbit. A nationwide team of government and industry experts is methodically doing the detailed planning that will deliver the nation's new capability for human spaceflight. The Ares 1 launch vehicle team builds on powerful heritage hardware and knowledge with the added advantage of high-technology network tools to share information with partners across the country. This disciplined approach to design and analysis is part of the team's commitment to systems engineering and integration to reduce the risk that is inherent in an effort of this magnitude. The ARES team is preparing for the Crew launch vehicle's first major milestone, the System Requirements Review, where research performed to date will be evaluated before proceeding to the more detailed design phase. The test what you fly and fly what you test philosophy is evidenced in preparations being made for the first ARES flight test in 2009, just 33 months from now. Calling on the expertise and resources of multiple NASA centers, the Flight and Integrated Test Team is preparing the desired objectives for suborbital and orbital flights that will inform design decisions and refine mission operation scenarios. Suborbital flight tests will be conducted in the next few years using lower fidelity hardware that approximates mass and weight. The Glenn Research Center is fabricating a simulated upper stage to fly on a reusable solid rocket booster first stage during the inaugural ARES 1-1 flight. While preparing to fly even more realistic hardware and then actual vehicles, this early testing in real-world environments will allow engineers to update the integrated vehicle stack design as work progresses from design and development to fielding. Flight testing also will ensure that the system is safe and fully operational before astronauts begin traveling to various destinations via the ARES 1. The upper stage mock-up and flight test planning are two examples of the progress that is being made by the ARES 1 team. In April 2006, a well-attended open house was held at the one-of-a-kind Michoud Assembly Facility in New Orleans. Co-sponsored by the Louisiana Economic Development Office, this event provided an opportunity for NASA to refine its acquisition strategy by soliciting industry inputs. The Michoud facility has been producing the Space Shuttle external tank for over 25 years and built the Saturn S-1C and S-1B booster stages in the Apollo era. Making a seamless transition from design to production and working with the shuttle program for a smooth handoff from external tank processing to ARES tank manufacturing is in the active planning stage. This facility layout shows some initial processing flows, including using the latest in friction stir welding technology. This concept shows how liquid hydrogen tanks are built, and then the overall stage is assembled. These will be shipped by barge to the Kennedy Space Center for further processing at the launch site. The Ares 1 upper stage will be the most advanced ever built and flown. Friction stir welding bonds two pieces of metal into a solid seam. This automated process can be performed either vertically or horizontally on very large structural materials and shapes, whether flat or curved. The Ares 1 materials team recently perfected an innovative technique to plug the hole at the end of the friction stir weld. This solid-state friction stir welding process was developed at the Marshall Center. In addition to building the flight simulation hardware, the Glenn Research Center also is developing the actuator and the thrust vector control system that will allow the J2X engine to move and keep the upper stage on track through flight. Glenn engineers are developing the power systems and sensors as well. Just as the Ares 1 upper stage structure research and development will benefit the Ares 5 cargo launch vehicle Earth departure stage, the human-rated J2X engine now being designed will power the upper stages for both vehicles, saving time and money. The J2X is an evolution of the Apollo Saturn V upper stage engines that sent spacecraft on course during America's previous lunar missions. The J2X engine team has reviewed historical records and consulted with Apollo-era veterans to apply lessons learned and mitigate the risk of developing a new engine in a short time frame. The recent X-33 experimental vehicle used J2S turbo machinery, shown being tested at the Stennis Space Center. The upper stage engine team is collecting information from these tests and other sources, such as the original Saturn V databases, to put the engine on track for its power pack tests in about a year. Stennis also is conducting tests on the integrated powerhead demonstrator, which is roughly the same thrust class as the J2X. Some key technology improvements in channel wall chambers and nozzles being validated now may be directly applied to the human-rated engine that will perform vehicle circularization and translunar injection. Early hardware testing to inform design analysis has begun at the Marshall Center with the J2X injector test. This analysis helps designers anchor complex models, leading to detailed component testing. Again, the J2X will be a one-engine development to serve both the crew and cargo launch vehicles, putting the crew exploration vehicle into Earth orbit and the Earth departure stage lunar lander combination first into Earth orbit, then into lunar orbit. This means that the engine will have to fire a number of times, including while in flight, and again while in space. To replicate these extreme operating environments, testing will be performed both on the ground at Stennis and in unique Glenn facilities that simulate in-space conditions. The Ares 1 first stage and the Ares 5 core propulsion stage both will be powered by a 5-segment reusable solid rocket booster, evolved from current shuttle hardware. This heritage means that each 4-segment shuttle test firing provides information for the 5-segment version. Hundreds of sensors capture data during ground testing and mission flights. In the near future, specific data such as roll control dynamics will be collected for the Ares 1 as well. And commonality between the two vehicles reduces complexity and logistics. Some of the hardware for the nozzle components of the 5-segment booster have been fabricated, and a mock-up of the new forward structure that allows the first stage to attach to the upper stage has been fabricated. In August, the Ares 1 booster recovery system pilot parachute will be tested at the Yuma Proving Grounds. The Ares 5 cargo launch vehicle core propulsion stage also will be powered by the RS-68, which is the largest liquid hydrogen liquid oxygen engine in existence. A cluster of 5 engines, in combination with 2 5-segment reusable solid rocket boosters, will lift this vehicle and its heavy exploration payloads into Earth orbit for journeys to the Moon, Mars, and beyond. The relatively simple and low-cost RS-68 core stage engine currently powers the Air Force's Delta IV Evolved Expendable Launch Vehicle. NASA is exploring partnerships with the Air Force for engine upgrades that are now in progress. Subsequent flights of this power plant on the Delta IV will provide valuable information. Stennis will test both the RS-68 and the J2X engines. Lessons learned from one engine effort will be applied to the other to reduce near-term development investments and long-term operations costs, as well as to increase the probability of mission success.